This video covers Part 1 of Section 3.6, Indirect Proofs of Conditional Statements. In Section 3.4, we looked at direct proofs of a conditional statement of the form, for all x, p of x implies q of x. To prove such a statement, we start by supposing x is an arbitrary element of the domain. We then need to show that the conditional propositional function, p of x implies q of x, must be true for this arbitrary element x. From the definition, we know that a conditional statement is false only when the hypothesis is true and the conclusion is false. So to prove that p of x implies q of x is true, we must then show that whenever the hypothesis p of x is true, the conclusion q of x must also be true. In a direct proof of p of x implies q of x, we start with the hypothesis and then make one deduction after another until we can conclude that the conclusion must then be true. In an indirect proof, we show that a statement is true by showing that a logically equivalent statement must be true. Since logically equivalent statements always have the same truth value, if we can show the equivalent statement is true, then it follows that the original statement must also be true. As we'll see, it is often easier to prove the equivalent statement, and in many cases we can only prove the equivalent statement and not the original statement. Since a conditional statement is logically equivalent to its contrapositive, then in order to prove a statement which has the form for all x, p of x implies q of x, we may instead prove the contrapositive statement, for all x, not q of x implies not p of x. This method of proof of a conditional statement is called a proof by contrapositive. Here's the procedure for a proof by contrapositive of a statement of the form for all x, p of x implies q of x. We first form the contrapositive of the given statement. So for the contrapositive, we flip the hypothesis and conclusion and negate them so that we obtain for all x, not q of x implies not p of x. We then carry out the steps for a direct proof of this contrapositive statement. So our first step is to specify our variables. We suppose x is an arbitrary but fixed element of our domain. For our second step, we're going to suppose the hypothesis is true. So in this case, we suppose the hypothesis not q of x of the contrapositive statement is true for the arbitrary element x. And for our third step, we show that our conclusion is true. So we need to show that the conclusion, not p of x of the contrapositive statement, must then be true for this element x using definitions, axioms, previously established results, together with the rules of logic. We've already seen some examples of proofs by contrapositive in previous sections. For instance, in order to show that a function f from x to y is injective, we usually use the contrapositive version of the statement in the definition. The reason for using the contrapositive version of the statement is that it is often easier to prove an equality, x1 equals x2, after assuming an equality, f of x1 equals f of x2, than it is to prove an inequality, f of x1 is not equal to f of x2, after assuming an inequality, x1 is not equal to x2. With many statements, the contrapositive statement is easier to prove than the original statement. Unfortunately, it's often not clear that this is the case until we actually attempt a direct proof and are unsuccessful. As a general guideline, we usually first attempt a direct proof. If it doesn't seem to be working out, we can then attempt a proof by contrapositive or some other method of proof, as we'll see later in the course. For our first example, let's use a proof by contrapositive to prove the following statement. For all positive real numbers x, y, and a, if xy is greater than a squared, then x is greater than a or y is greater than a. As usual, we first write out our symbolic form, which is for all x, y, and a are greater than 0, xy greater than a squared implies x is greater than a or y is greater than a. This is equivalent to the contrapositive statement for all x, y, and a greater than 0, x is less than or equal to a, and y is less than or equal to a implies xy is less than or equal to a squared. So now to prove the statement, we use a direct proof of this contrapositive statement. For our first step, we specify our variables. We suppose x, y, and a are arbitrary positive real numbers. We suppose the hypothesis, x is less than or equal to a and y is less than or equal to a. We then need to show our conclusion, xy is less than or equal to a squared. Since y is positive and x is less than or equal to a, then multiplying both sides of our first hypothesis, x less than or equal to a by y, we obtain xy is less than or equal to ay. Since a is positive and y is less than or equal to a, then multiplying both sides of our second hypothesis, y less than or equal to a by a, we obtain ay is less than or equal to a squared. We can then combine these two inequalities. Since xy is less than or equal to ay and ay is less than or equal to a squared, then by the transitive property of inequalities, we obtain xy is less than or equal to a squared. This is the conclusion of our contrapositive statement. So this proves the contrapositive statement, and we can therefore conclude that the original statement is true. Now suppose we attempt a direct proof of the statement in this example. We start by again supposing x, y, and a are arbitrary positive real numbers. We suppose the hypothesis xy is greater than a squared. We then need to show the conclusion x is greater than a or y is greater than a. At this point in the proof, it's not clear how to proceed. When we prove the contrapositive statement, we started with the two inequalities x is less than or equal to a and y is less than or equal to a, and we were able to combine these using our properties of inequalities to obtain the inequality xy is less than or equal to a squared. For the direct proof, we are starting with the single inequality xy is greater than a squared, and we have to somehow separate the variables or eliminate one of the variables to obtain either of our two conclusions, x is greater than a or y is greater than a. There just doesn't seem to be a valid procedure that will enable us to do this, and so it seems that the direct proof fails. Now note that in writing any proof, you want to keep the reader informed. This means stating at the outset the type of proof you're using. For instance, at the beginning of a proof by contrapositive, you want to announce that you are using this method to the reader. Otherwise, it may take a reader several lines to realize what's going on. In section 3.2, we prove that the square of any odd integer is odd, or for all odd integers n squared is odd. We can rewrite this as a conditional statement for all integers n. If n is odd, then n squared is odd, where the domain is taken to be the set of all integers z instead of the set of all odd integers. Let's review the proof of this statement as a prelude to proving the converse statement. So we want to prove for all integers n, if n is odd, then n squared is odd. This has symbolic form for all n and z. N is odd implies n squared is odd. We use a proof by arbitrary element, so we start by specifying our variables. So we suppose n is an arbitrary integer. We suppose our hypothesis, n is odd. We then need to show our conclusion, n squared is odd. To show this, we need to show there exists an integer k such that n squared is equal to 2k plus 1, or in symbolic form there exists a k in z such that n squared equals 2k plus 1. So now we're doing proving an existential statement. So we'll set up our two columns for an existential proof. And we start with our hypothesis. Since n is odd, then there exists an integer L such that n is equal to 2L plus 1. We square both sides of this equation and we obtain n squared is 2L plus 1 quantity squared, which works out to 4L squared plus 4L plus 1. Factoring a 2 out of the first two terms, we obtain 2 times the quantity 2L squared plus 2L plus 1. And now this resembles our propositional function n squared equal 2k plus 1 with k equal to 2L squared plus 2L. So we'll choose k to be 2L squared plus 2L. We're now ready to move over to the right-hand column, and for our domain we need to show that k is in z. Since L is an integer and z is closed under multiplication and addition, then we know that k equal 2L squared plus 2L is in z. And from the work on the left, we have n squared is equal to 2 times the quantity 2L squared plus 2L plus 1, and this is equal to 2k plus 1. So the propositional function holds. So this proves the existential statement, and so thus n squared is odd. We now want to consider the proof of the converse statement, which is also true. So first we're going to restrict our domain to just the positive integers, and as you'll see, we need to assume this to simplify part of our proof. So we're going to consider the statement for all positive integers n, if n squared is odd, then n is odd. So let's suppose we try to prove this result using a direct proof, analogous to the proof in our preceding example. We want to determine where the attempt fails, if indeed it does fail. So our symbolic form is for all n and n squared is odd implies n is odd. So we suppose n is an arbitrary positive integer, suppose n squared is odd. We then need to show that n is odd. To show this, we need to show there exists an integer k such that n is equal to 2k plus 1, or in symbolic form, there exists a k in z such that n is equal to 2k plus 1. So now to prove this existential statement, we'll set up our two columns, and we can use our hypothesis. Since n squared is odd, then there exists an integer j such that n squared is equal to 2j plus 1. Now in the proof of the original statement, we had n is equal to 2l plus 1, and we squared both sides to obtain an expression for n squared. And from that, we were able to determine what we should choose for k. In this proof, we have n squared is equal to 2j plus 1, and our propositional function is n is equal to 2k plus 1. So the natural thing to attempt to do is, instead of squaring both sides, to take the square root of both sides of this equation. So taking the square root of both sides of this equation, since n is positive, we'll have the square root of n squared is just equal to n, and so we obtain n is equal to the square root of 2j plus 1. Now, since we want a k satisfying to n is equal to 2k plus 1, we can set this expression for n equal to 2k plus 1 and solve for k. So we'll have 2k plus 1 is equal to the square root of 2j plus 1, and then take the 1 over to the other side, divide both sides by 2, we obtain k is equal to 1/2 times the quantity, negative 1, plus the square root of 2j plus 1. So now we've found our k. We know this satisfies the propositional function because we actually chose k using the propositional function. The problem arises with the domain, so we need to verify that our k is actually an integer. So we know from our hypothesis that j is an integer. However, there does not seem to be any way to conclude from the fact that j is an integer that k is equal to 1/2 times negative 1 plus the square root of 2j plus 1 is an integer. Knowing that j is an integer does not allow us to conclude that the square root of 2j plus 1 is an integer, much less that our expression for k is an integer. Now, in fact, since n is equal to square root of 2j plus 1, then we do know that square root of 2j plus 1 is an integer. However, we still cannot conclude that k is equal to 1/2 times the quantity negative 1 plus n is an integer. In order to conclude this, we would need to know that negative 1 plus n is an even integer, which means that n is an odd integer, but this is exactly what we are trying to prove. At this point, there does not appear to be any way to proceed further. We then have two choices: begin the proof over with a different approach or give up. Since there's no quitting in Math 280, we choose starting over with a different approach. In particular, we can try a proof by contrapositive. So we'll start over again with our example, and this time we'll remove our restriction that n is a positive integer. So we want to prove for all integers n, if n squared is odd, then n is odd. So our symbolic form is, for all n in z, n squared is odd implies n is odd. We're going to use a proof by contrapositive, as I already mentioned. So we start by writing the contrapositive statement, which is going to be for all n in z, not n is odd implies not n squared is odd. And this is equivalent to, for all n in z, n is even implies n squared is even. So we'll start with a proof by arbitrary element. We suppose n is an arbitrary integer. We suppose the hypothesis that n is even. We need to show the conclusion, n squared is even. To show this, we need to show there exists an integer k such that n squared is equal to 2k, or in symbolic form, there exists a k in z such that n squared is equal to 2k. So we'll start our existential proof. According to our hypothesis, since n is even, then there exists an integer l such that n is equal to 2l. Our propositional function now is n squared is equal to 2k. So we square both sides of our hypothesis, and we obtain n squared is equal to quantity 2l squared, which is 4l squared. We can factor 2 out of that, and we obtain 2 times the quantity 2l squared. So now this looks like our propositional function, n squared is equal to 2k, with k equal to 2l squared. So we choose k to be 2l squared. We've now found our k, and so we're ready to go over to the right-hand column. Since L is an integer and Z is closed under multiplication, then as usual, we obtain K equal to L squared is an integer. And from the work on the left, we have N squared is equal to 2 times the quantity 2L squared, which is equal to 2K, so the propositional function holds. So this proves our existential statement, and so thus N squared is even. This proves the contrapositive statement, so we can then conclude that the original statement is true. Here's one more example of a statement which can be proved using a proof by contrapositive. This turns out to be a frequently used lemma in advanced calculus. So we want to prove for all non-negative real numbers x, if x is less than epsilon for all epsilon greater than 0, then x is equal to 0. We first want to write the symbolic form for this statement. Now note that the statement includes two universal quantifiers, one on x and the other on epsilon. We're somewhat used to writing all the quantifiers out in front of the propositional function, so we might think of writing the symbolic form as for all x greater than or equal to 0, for all epsilon greater than 0, x is less than epsilon implies x is equal to 0. However, if you examine the wording of the statement carefully, you should see that this is not what is intended. The quantifier on epsilon is intended to be part of the hypothesis only, and that's specifically why it's included after the statement x is less than epsilon. So putting the quantifier on epsilon with the hypothesis means that the correct symbolic form is for all x greater than or equal to 0, for all epsilon greater than 0, x is less than epsilon implies x is equal to 0. It's very important to start with a correct symbolic form. You cannot prove a statement if what you set out to prove is incorrect to begin with. So we're now ready to start the proof. We have a universal statement, so we'll use a proof by arbitrary element. Whoops, sorry, let me back up. We're going to use a proof by contrapositive, as I said. So we start by writing the contrapositive statement. So the contrapositive statement is for all x greater than or equal to 0, not x is equal to 0 implies not for all epsilon greater than 0, x is less than epsilon. So we flip the hypothesis and conclusion and we negate each of them. Now the negation of x is equal to 0 is just x is not equal to 0. The negation of for all epsilon greater than 0, x is less than epsilon is going to be the existential statement, there exists an epsilon greater than 0 such that x is greater than or equal to epsilon. Okay, so now we're ready to start the proof. So we'll suppose x is an arbitrary non-negative real number. We'll suppose our hypothesis, x is not equal to 0. We then need to show our conclusion, there exists an epsilon greater than 0 such that x is greater than or equal to epsilon. That is, we need to show there exists a positive real number epsilon such that x is greater than or equal to epsilon. So we're proving an existential statement now, so we'll set up our two columns for an existential proof. So in the left-hand column we need to find an epsilon, and in the right-hand column we need to verify that our epsilon satisfies our two conditions, the domain, epsilon is supposed to be a positive real number, and our propositional function, x is greater than or equal to epsilon. Now our hypothesis says that x is non-negative, but also that x is not equal to 0. So we can then conclude that x is actually strictly greater than 0. This means that x lies to the right of 0 on a number line. Now we're looking for an epsilon, which is a positive number, satisfying epsilon is less than x. That is, x is still to the right of epsilon. So if we draw a picture of a number line, we can it'll help us visualize what's going on. So we have 0 on the number line, x lies to the right of 0 on the number line, and x is also supposed to lie to the right of epsilon. So this means that epsilon must lie in the interval between 0 and x on the number line. So for our choice of epsilon, we can basically choose any number epsilon which lies in the interval from 0 to x. For instance, we can choose epsilon to be the midpoint between 0 and x, or epsilon is equal to 1/2 x. Or you can choose any other fraction less than 1 times x. Okay. So we now have our epsilon. So we need to verify our two conditions. For our domain, since x is a positive real number, then it's clear that epsilon equal 1/2 x is also a positive real number. So our domain condition is satisfied. For the propositional function, we know that since x is greater than 0, then x is going to be greater than or equal to 1/2 x, which is our choice of epsilon. So our propositional function, x is greater than or equal to epsilon, is satisfied. So this proves our existential statement, which proves the contrapositive statement, and so proves the original statement. Here's how we can actually apply this result. Suppose we have some quantity x that we know is non-negative but want to show equals 0. According to this result, if we can show the hypothesis for all epsilon greater than 0, x is less than epsilon holds, that is, x is less than epsilon for all positive numbers epsilon, then we can conclude that x is equal to 0. It turns out that in some applications it may be easier to show this hypothesis holds than to show that x is equal to 0 directly. As I mentioned already, this is a result which is a lemma in advanced calculus, and so when you take 350, you're going to encounter it there.